So now we're going to look at is a slightly different approach to hypothesis testing. The approach we learned before was called the classical approach. There is another approach that can be used, and we will use on occasion, called the p-value approach. And really all it does is it kind of changes, ultimately how we make our decision. But it only changes steps 3 and 4. So we would still create the same hypotheses, find the same test statistic. The difference is rather than finding a critical value, critical region, and drawing that picture and seeing if the test statistic falls in the region, we instead calculate an area called the p-value based on that test statistic. So basically, step 3 is a p-value of the thing we did in step 2. And that means you're creating the same bell-shaped curve, but instead you're just saying, I know this boundary is that number we get from step 2. And I'm asking what's the area, either to its left, to its right, or in this case of the two-tail test, to either side of the positive or the negative of that value. And the idea here is you're finding an area that you will then compare to alpha. So rather than letting alpha be the thing that determines the tail you draw, you're finding the area based on the value we got from that step 2, and then comparing that value to alpha. Notice it's either this tail, or in the two-tailed test. When you know you're in a two-tailed test, you are actually adding up, summing up the areas of both left of and right of whatever that value would be. Keeping in mind, it has to be the positive and the negative of it. You only get one whenever you do step 2. So you'll calculate that test statistic in step 2, but for a two-tailed test, you will use it as both a left and a right boundary. That's the difference. And then those values, that p-value you get, you'll compare directly to alpha, and if the p-value is less than alpha, you'll reject the null. If it's greater than, you will not reject it. To try to make quick sense of this, if you understand the classic approach from the previous page, think of it this way. Remember, this line represents your test statistic. And we're saying that if this area, right, if this tail, if that that p-value is less than alpha, reject the null. Well, what does that mean? That means that this tail has to be smaller than the tail that would be made by the critical value if you found it. Well, that means the critical value would need to be further over here, somewhere over here, so that its tail of alpha was bigger than this tail of the p-value. It's just another way of representing the exact same information. There's no difference here. It's just a different way to calculate it. And going forward, some statistics tend to rely more so on the p-value for various things. That's one reason we're showing it to you. But the overall idea is exactly the same. If your test statistic has a small p-value that's smaller than alpha, all that means is this border, this boundary, this position is inside of that bigger tail that was made by alpha. Thus, it's in the rejection or critical region, and that's why we're rejecting. So that's why this works. If your p-value is less than alpha, your test statistics tail is smaller than your critical region's tail, and that's why it's inside, and that's why you reject. Okay? Now, like I said, ultimately this changes very little about our problem, except those steps 3 and 4, really. So, jumping into this one. In 2006, 31.5% of all live births in the United States were to mothers under 20 years of age. A sociologist claims that the births to mothers under 20 years of age is decreasing. She conducts a simple random sample of 102 births and finds that 27 of them were to mothers under 20 years of age. Test the sociologist's claim at alpha of 0.01 level significance. Now, the next 2 pages, we're going to do this with each approach. So, this approach we'll use as the same from earlier, the one we did on the previous video on page 10. Then we'll do this exact same problem again and just twist the steps to use the p-value approach. So, first and foremost, this is a test about proportion. We do need to test it or check it. So the NP1 minus P, actually I normally call this a check, not a test. So checking this, our sample size is 102, and then the values of P are the 0.315 and 0.685. And that's coming out to 22 and some change, which is bigger than 10. which I should say at least 10. So we're good. So now, let's jump into the hypotheses. The null and alternative, where the null is that it was currently believed to be 0.315, and we're proposing it's decreasing, so that means we're looking at less than 0.315. So there's hypotheses. I'll go ahead and label those. Now we need step 2 of our test statistic. So that's going to be our Z0 from that formula. All right, so for p hat, we need p hat again because they just gave us the 27 out of 102. So p hat of 27 out of 102, 0.2647. P naught is the currently believed value of 0.315. And again, sample size is the 102. So let's see what we get there for a test statistic. All right, getting negative 1.09. So again, that is our, what we would call Z0, or again, to abbreviate, test statistic. So with a classical approach, our next step is to find that critical value and region. Now, with a less than alternative, we have a left tail test. With an alpha of 0.01, we know the area of that tail is 0.01. And so to find that critical value, the boundary of that tail, we just need inverse norm of 0.01, giving us negative 2.326. So that's our critical value. So with that, we can move on to the decision, where we've got a left tail at negative 2.326 is the boundary of that tail. Our test statistic is negative 1.09. So starting at 0, negative 1.09 is not quite there, right? It's not to the left of, it's not lower than, negative 1.09 is not smaller than negative 2.36. So it's here, it's somewhere outside of that critical region. So again, we also call a rejection region. So if you're not in there, then we're going to choose to not reject the null hypothesis because our test statistic was not within that region. Okay? And so that leads us to our conclusion sentence, starting it off with the level of significance. A level of significance of 0.01. We decided that this evidence was not strong enough to reject. So we will be saying there is not sufficient evidence to support the claim that the population proportion of all live births in America to mothers under 20 is less than 31.5%. Because again, that was the claim. We claimed that it had been decreased. We claimed that it was under that. So we're saying there's not sufficient evidence to support that claim, that the population birth population percentage of all live births in America to mothers under 20 was less than that 31.5%. So now, to take a look at basically all the steps, we won't write the sentences again because it'll be the exact same sentence because it's the exact same question. This is the exact same information. We would still do the check. All right, I'm going to say the check is the same. Now, to the hypotheses. Still involving the proportion, believed to be 0.315, proposed to be less than 0.315, nothing changes there. To find our test statistic, that is still the exact same Z0 formula. The P hat minus P naught over absolutely the exact same formula, nothing there changes. So we'll just use that same number from before. But we get to the next step. And this now, instead of being a critical value step, is a p-value step. And so we use this alternative hypothesis to tell us right there, that tells us this was going to be a left tail test. This being our test statistic tells us let's draw a picture with negative 1.09, but we're looking at shading to its left. We want to figure out that area. Now, if you have a picture of a bell-shaped curve, normal curve, where you know the z-score and want the area, remember that's not inverse norm, that's our other normal calculator function of normal CDF. And so in this case, since it's going left forever, we can use like negative 10, and we can ask for the normal CDF of negative 10 to negative 1.09. And that's giving me 0.1379. I'm going to take that 4 places because this is an area under the curve, which is effectively the same as talking about probability. So 0.1379 being the area of that curve, that is our p-value for this problem. And so for our decision step, we now compare the p-value to alpha. And we've got 0.1379, but our alpha was only 0.01. So the p-value is definitely much larger than alpha. And so the situation, the scenario for p-value, if the p-value is larger than alpha, we said we do not reject the null. And again, think of it this way. The p-value being larger means your test statistic is out here with a large tail to its left, 13, almost 14% to its left. We would have needed our test statistic to fall in a tail that only had 1% to its left. That's going to be a very small tail, a very small critical region or rejection region. This value would not have fallen inside of that small tail because it's got a much larger tail. So if our critical value, if our test statistic has a large tail, it's not in that rejection region. If this had been a very small tail, very tiny p-value, and it had been less than alpha, it would have been the idea that our test statistic would have been inside that region, and then that's why we reject. So that's the logic and how you can kind of compare the classical versus the p-value approach. And then for the conclusion, again, the exact same wording, nothing changes about this problem, as you noticed. Even that stayed the same, this calculation's the same. It's simply what you do with that p-value or that that test statistic and how you compare it to alpha. That are the things that change.